asking some questions if there are any doubts, but just to very briefly recap, what I was doing yesterday was mentioning how the ADS3 times S3 times T4 background is a very good example to study the ADS-CFT correspondence beyond the supergravity limit in the stringy regime. And the way you do that is the reason you can do that is because of the presence of NS flux, quantized units of NS flux, which can go from, which take all positive integer values. Very large values of K correspond to the supergravity limit. But if you are at finite values of K, you can look at a sigma model, which is essentially an SL2R level K plus 2 times SU2 level K minus 2 times the T4 or K3 sigma model. So this is the NSR formulation, and I explained how Maldacena and Oguri showed how this is quite subtle. The set of physical states in this theory is quite subtle because of the non-compact nature of the SL2R, and in particular, I described the states or the affine representations that would be needed to describe the spectrum, and I sort of mathematically explained how both the continuous representations as well as the discrete representations enter, and you have to build an affine tower on these. But there is a new notion of this spectral flow, which generates even more representations of the affine algebra, which are not highest weight representations, but nevertheless are Virasoro primaries and therefore are well-defined string physical states. And these are labeled by a positive integer W, which and the corresponding representations were what were denoted over here. And these representations in terms of the original modes, they had this funny property that some of the positive modes don't annihilate the ground state, whereas some negative modes do. And these are like, so there's a shift, and that's what this n plus w and minus w captures. And then there are shifts also in the J3 eigenvalues and L0. So this was roughly what I was describing yesterday. But if you have any immediate questions, please ask at this stage.
I have a question.
Sure.
So is it unique some tip? I mean, is it unique? And is there any other like some new generator that preserve algebra but change the states? Or
I'm sorry, I didn't quite understand. Is what unique?
I mean, this kind of a new definition of a generator, is it unique? Like you can, someone find some very other like a combination to preserve the algebra. So
right. I think as an automorphism, as what is called an outer automorphism of the SL2R, I think this is essentially the unique automorphism that one has, because you want linear automorphism which preserves the commutation relations. So preserving the commutation relations is not an easy thing to achieve. If I just make some arbitrary redefinitions. So I think this is, so in that sense, as an automorphism of the SL2R, the spectral flow has a very special role. And secondly, in terms of, you might ask why include these states and so on. Well, there are many reasons, and Maldacena and Oguri give several reasons in their first paper, including some physical ones, which I'll very briefly mention, what the interpretation of these winding strings are, these spectrally flowed states are in terms of classical solutions. But more generally, in their second paper, they computed the path integral of the SL2R level K theory. And in computing the path integral, they showed that the path integral is this is more like a Hamiltonian approach, but that's more like a Lagrangian approach. You start with the Wezminowittian model, and if you include all the appropriate sectors, if you compute the thermal partition function, including all the winding modes and so on, you find that the partition function does include all these states. So the modular invariant partition function, you need to include these. And then in their third paper, they went on to show how in the 3-point functions also you generate these states, even if you started with so you need these for sort of completeness of the spectrum. So so let me mention this again. This picture is from Maldacena and Oguri. What, in fact, the first part of their paper, they do a semi-classical analysis of the string solutions in ADS3, and they find that you have a class of solutions of finite energy, which correspond to what they call short strings. So the simplest solution are, of course, particle-like trajectories which go like this. But what they showed is that starting from those short strings, which are like time-like geodesics, you can make these longer strings, which are essentially winding around they are particle-like, so they are like short strings in that sense. So you should think of these as some short trajectories going around like this, but they kind of have they wind around W times. Then there are another class of strings another class of solutions which start with space-like geodesics and then consider the spectral flow on them. So there's a classical analog of spectral flow you can define, namely, starting with a given solution, you can define a new solution, which is essentially what this spectral flow does at the quantum level. You multiply it by some appropriate power of the worldsheet variables to generate a new solution. And these solutions are essentially what are called long strings. They have some radial momentum. So they have some momentum. So they kind of come in from infinity and they sort of wind the W times in some ways. And they come in from infinity, they have a momentum, they kind of collapse, then expand back and so on. So that's the physical interpretation of these strings. These short strings correspond to these representations, the discrete states, and they are discrete in some ways because these are like particles in a box essentially, whereas these are continuum states. They are the ones labeled by the continuum radial momentum P, and they are continuous because the momentum can take any value. That was the J equals to half plus IP. So these correspond to these spectral flow representations of the continuous family of SL2R. Okay, so I don't have the time to go into more detail, but you can look at the relevant initial couple of sections of the first paper of Maldacena and Oguri that I had mentioned last time when given the reference last time, and you will see the details of this. Okay, so
I have a question on this representation. And from the point of the representation theory, are they complete? Like, what about the completeness relation? Like,
there are many. Well, it depends on which represent. If you're looking at just SL2R, the global symmetry, then of course, there are many notions of completeness in the language of representation theory. If you're looking at the L2 normalizable wave functions, then the continuous and the short, the original CJ lambda and the DJs are essentially give you a complete set of L2 normalizable unitary reducible representations. And then, of course, we are considering the not the global symmetry, but the affine symmetry. And as I said, I think the only notion you can talk about there is of modular invariance in the context of the one loop path integral. And in that, you see that these give you the complete set of states. That's what I was meaning when I said earlier that the one loop path integral automatically includes these states as well. Yeah, so that's the situation. I want to say just one more thing, just a physical picture about these long string solutions. So normally you might have thought, how come you can have long strings which are almost stretched towards the boundary? And the answer is that because you would think that costs a lot of energy, it costs infinite energy as you move towards the boundary, because these strings are infinitely long. But that's the interesting thing in ADS3 with NS flux, that the H flux sort of compensates for the tension, the string tension. It's a bit like having an open string in an electric field. You know that the electric field will try to pull apart the two endpoints of the open string, and it will counterbalance with the tension. And so by making the electric field very large, almost the same as the tension, you can kind of make the string effectively tensionless or with finite energy. So something like that is what is happening with the long strings over here. So it balances, the energy actually balances out. And you can see this from the classical action as well. There are, in fact, we will see later, maybe tomorrow, that the classical solutions are like holomorphic strings. So the holomorphic maps actually carry almost zero action in the limit of at least in the tensionless limit. They'll have zero action, otherwise they carry some small action. So there's one thing one important remark I want to make over here, which is that so what you see from this is that the dual CFT2 must have a continuous spectrum. Of states labeled by, labeled by the momentum.
Before going to the holographic dual, may I ask a few questions on these pictures?
Sure. Yeah, 1 second. Let me just write this sentence down.
Yeah, sure. Sorry to interrupt you.
So yeah, go ahead, please.
So as far as I understand, so J is some kind of winding number, lambda a kind of momentum.
The W is like a winding number.
W is the winding. I see. And so what are the interpretation of J and lambda?
So in this long string, J was equal to half plus IP. And this P is this momentum that I was, so you can think of P as the radial momentum. So all these states, they carry some radial momentum. These are string states. That's why they're kind of expanding, collapsing. They kind of bounce back in some ways. So this radial momentum, the magnitude is what is P over here, and that's what J is for the continuous string. Here in this case, of course, J takes discrete values, and these are like the J's that you have. You can think of these as the center of mass momentum of the string. So one way to actually, I didn't stress this aspect, but you should kind of think of J plus minus as like the analog of del X plus del X minus in flat space. And maybe then there is J3, which is another direction, del X3. So that these are in the large K limit, these go over to flat space. And you should think of these currents as essentially the usual oscillator modes of the string. So that's what the J plus minuses are, and the ground state labels, this corresponds to the short string sectors essentially go over to the usual short strings that you have in flat space. So they will be just, this J is just labeling the center of mass momentum in that limit. The second Casimir essentially becomes like a momentum p square. But in this, these long strings are objects that are not present in flat space, and they are essentially new representations. And that's what this these representations are, and that's because of the presence of this flux, and you get these different winding modes. But these are sort of more familiar sort of short string excitations.
And so lambda is related to the flux, or?
Lambda is like a J3 eigenvalue, you know, so this is J30 eigenvalue. So you can think of it as one of the momenta, components of the momentum. If the Casimir is like the total momentum square, at least in these three directions of ADS3. But there is one commuting object, which is in SL2R. Of course, there's only one J30 which you can write as a commuting momentum. So that's like one component of the momentum. Yeah.
I see. Thank you.
Yeah. So what I wanted to say here was just that an immediate implication of this is that so far we have just looked at the ADS3 string theory and quantized it. But an immediate implication from the fact that there is a continuous spectrum of strings, long strings like this, labeled by P. By the way, I should say something, this lambda, in response to the previous question, this lambda, or in this case, J and lambda are the same because there's only one quantum number here. These get fixed. So in the case of the short string, these and this get fixed by the Virasoro on-shell condition. So that's what fixes these momenta. So the only, this radial momentum will not get fixed. So that's an additional parameter that's there in these long strings, which is not present in flat space, like I said. So there's a continuous spectrum of states, whereas this has a discrete spectrum. Here you get a discrete spectrum of physical states, whereas this will have a continuous spectrum, which is labeled essentially by this radial momentum P or this J, and therefore you have a somewhat singular CFT. So this implies the somewhat singular CFT because usually, at least the usual unitary CFTs that you consider in two dimensions typically have a discrete spectrum of states. And you have, it's only theories like Liouville and so on, which don't have good vacuum, that you have continuous spectrum of states. So somehow the thinking was always that this corresponds to some singular point in the CFT moduli space, because remember I told you that this, so there was always a question, where is this on the moduli space of this symmetric orbifold? Let's say T4 to the n mod Sn. Where do we find it in that moduli space? But because this seems to, at least at the free point, this is a perfectly well-defined CFT. You're just taking a T4 CFT, which has a discrete spectrum, and orbifolding it. You don't get any continuous, this is a discrete orbifold. You don't get any continuous spectrum out of it, at least at the free point. And you maybe you deform the theory far away. There are perhaps some singular points. So, but it was always a bit of a puzzle as to how this can be on the moduli space, or where is it on the moduli space. But at any rate, people seem to agree that definitely the NSNS flux has nothing to do with the symmetric orbifold. So that's what was the folklore until maybe a couple of years ago, where when we pointed out that there's a loophole to this argument that the dual CFT must have a continuous spectrum of states, and that's what I will now talk about in this thing. So there will be a loophole in this argument, and that will happen for k equals to 1. And as someone already remarked, the k equals to 1 theory is something where you already see something funny happening at the level of the sigma model. The SU2 piece becomes -8 and so on. So now I will focus therefore on the k equals to 1 theory, which will be the analog of the tensionless limit. Is this clear?
Just to clarify, so so we are saying that there are continuous spectrum of states, and are we considering only long strings in this case?
No, you're talking about the general case about for generic K.
Yeah, for a generic K.
For generic K, you have both short and long strings. So you have a discrete spectrum as well as a continuous spectrum. So you have both.
Okay.
But the fact that the continuum exists comes from essentially these states. So as long as these states with non-zero P are present, there will be this continuum, and it would seem to suggest the dual CFT is what is called a singular CFT.
Okay, so are we saying that for k equal to 1, we only have the long strings, or?
We'll see. Okay, let me just say for the loophole for k equals to 1 will be that there will be only long strings with p equals to 0.
I see. Okay, thank you.
So this continuum will be absent for reasons that I will explain.
Great, thanks.
Okay.
Actually,
yeah,
yes.
go ahead.
Sorry, go ahead.
Was there a question? No.
Yeah, actually, I just wanted to make sure. So K was the number of NS5 brain, right?
Yes.
So it's a U1 gauge theory.
I mean, so you will have to look at, I mean, you're thinking now in the language of the dual D5 NS, D5, D1 system, right?
Yeah, right.
Right, yeah. So it will be a U1 gauge theory and Q5 instantons on that, which really is singular, but there's actually a desingularization, which comes from considering the NSNS. So it's actually a non-commutative U1 gauge theory, and so you have still a non-trivial modular space.
Thank you.
So okay, so the K. So as I said, and we already someone already remarked that for k equals to 1, the NSR description in terms of SL2R level K plus 2 plus SU2 level K minus 2 plus T4. This is not well defined. It's not well defined because you don't know what is SU2 level minus 1. People have tried to make sense of SU2 level minus 1 in different ways, but it's not easy to give an unambiguous characterization of that. So, so the NSR description is not obviously at least well defined, but at the same time, k equals to 1 is a physical case because it's the smallest amount of flux. But k equals to 1 is the smallest radius flux that you can have. Remember, the radius was proportional to the number of units of flux. So k equals to 1, smallest radius and flux. So must be physical. So how do you make sense of this? Maybe this particular description breaks down. So in fact, this is what you would call the tensionless limit. You would like to. So this is highly stringy. So to make sense of this, we go to what is called more like, again, there was a question earlier about a Green-Schwarz-like formulation. So there exists a Green-Schwarz-like formulation. In fact, more accurately, it's called the hybrid formulation, which due to Berkowitz, Waffer, and Witten from 98 or so, 98 or 99. So this this builds on a formalism due to Berkowitz, in which was originally done for R6 times T4, and you make a field redefinition. So make a field redefinition from the RNS variables. To the Green-Schwarz variables for 6 dimensions, keeping remaining 4 dimensions NSR. That's why it's called hybrid. So this is very well suited for this ADS3 times S3 case, because then you can make the space-time supersymmetry manifest. So space-time supersymmetry in 6D is manifest. Not the full 10D space-time supersymmetry, but for the ADS3 times S3 times T4 background, it's sufficient to look at the 6-dimensional part, the part associated to the ADS3 times S3. So this will be actually, let me, so Green-Schwarz like description. So this was originally done for R6 times T4, but then Berkowitz, Waffer, Witten generalized it to ADS3 times S3. So you have ADS3 times S3, you have a Green-Schwarz like description, and NSR, actually a topologically twisted version of the NSR description. Description for the T4. Okay, so so actually the reason Berkowitz, Waffer, Witten were using this was that this formalism is powerful enough that you can even describe Ramon-Ramon flux, though it's very complicated. It has various funny features like hosts mixing with the matter, etc. But this is this BVW, Berkowitz, Waffer, Witten approach is simplest when there's pure NS flux. let's say k units, like we are considering. So what form does this take? And so it's described in that case by, again, a Wessel-Witten model, but now it is one based on the supergroup. So the supergroup PSU1,1/2, this is K is the same K here, the number of units of NS flux. So it's a supergroup Wessel-Witten model with level K. Note that the PSU1,1/2 is the global symmetry. This supergroup is the global symmetry of the ADS3 times S3 piece. So I should have said over here, this described by this Wessel-Witten model, plus then there are the Gauss, and then the T4, the twisted T4 theory that I mentioned here, which continues to be in the NSR. So it's the Green-Schwarz-like part, which is described now by the supergroup, and this is the global symmetry of the ADS3 times S3 part. So for instance, the SU1,1, which is the same as SL2R, is and SU2, the R symmetry, SU2R. These are all, these belong to, these are the bosonic subgroups of PSU1,1/2. And the fermionic components are the space-time supersymmetries. So PSU1,1/2, you can think of, there's a bosonic and fermionic piece, and this is the SU2, and this is the SU1,1 or SL2R, and then there are the off-diagonal fermionic pieces. So that's what this supergroup is essentially. And this makes the space-time supersymmetry manifest, because our Wessel-Witten model has this as its global symmetry. So this is why it's Green-Schwarz-like. So that's this thing. So let me just say what the full string theory is. So the full string theory in this hybrid formulation is the PSU1,1/2 level K Wessel-Witten theory, and this has C equals to -2. I mean, it's not difficult to show that, but I don't have time to explain that in general. But this is actually independent of K. You can always show, you can show that this supergroup like this always has C equals to -2. Later, when we focus on the K equals to 1 theory, we will see very easily how that comes about. So then there's it has this plus the topologically twisted T4 theory. And that has C equals to 0 because it's topologically twisted. Then there are a set of ghosts that which are not very intuitive to set of ghosts. These are given by two bosonic fields, rho and sigma. These have a background with bosons with background charge. free bosons with background charge such that the central charge of rho is 28 and central charge of sigma is minus 26. The sigma host is easy to understand. The sigma host is the bosonization of the usual BC host system, of the BC super diffeomorphism. So that has C equals to minus 26. So you can write, for instance, like B is equal to e to the I sigma, and C is equal to e to the minus I sigma, something like this. So you see that the net central charge vanishes because you have -2, 0, and then from the ghosts you have +2 from this rho and sigma. So the rho and sigma can be thought of, the rho ghost can be thought of as some combination of the super diffeomorphism ghosts, which I don't have, which is not easy to explain. So the main point is that this string theory makes sense. The string background makes sense for all k. Is well defined for all k, including k equals to 1. So even though the NSR formulation broke down at k equals to 1, this hybrid or Green-Schwarz formulation is well defined for n equals to for k equals to 1. And this is what we will use and take as the definition of the k equals to 1 theory.
Also,
So,
can you also take a k equals 0 here?
Well, I mean, it would be trivial then. It's BSU 1,1/2 level 0 is essentially nothing. It has a 0 central charge. So it's not very clear. Yeah. So k equals to 0 is probably doesn't make sense as a string background.
You said the central charge. Sorry.
The central charge is -2 for k not equals to 0. For k equals to 0, it would be a bit trivial to, yeah. So that's this thing. And one way to understand the c equals to -2 is that the U1,1/2 theory always has central charge 0 because it has sort of vanishing and then you mod out by two U1s. That's what gives you the PS. The S is like usual, saying that the determinant is 1, and then the super determinant is 1, and the P is like an overall projective. It's the other U1. So one is the sum of the two U1s of the bosonic, and the other is the difference of the two U1s of the bosonic pieces over here. So so that's quotienting out by those two U1s reduces the central charge from 0 to -2. But we'll see that in the case of the free theory later, in the case of the k equals to 1 theory. Okay, so this, so we'll take this as the definition of the k equals to 1 theory. Because this Weissenmiller-Witten model makes sense. And in fact, the k equals to 1 theory is also special. It's well defined here, but you see from this this thing in the hybrid description. And the reason why it is special is that PSU has a free field description. I'm assuming many of you are familiar with basic CFD, and you know that SU2 level 1 has a free field description in terms of free fermions, right? And so similarly, in fact, you see over here the PSU 1,1/2 at level 1. It contains an SU2 level 1. There's an SU 1,1 at level 1. So it's not perhaps unexpected, and one can actually write it down very explicitly. So you can realize the free field. So this consists of two complex fermions, which are canonically conjugate. So two pairs of canonically conjugate fermions, I should say. So that's a bit like the SU2 piece. So I'll write that psi alpha So this is alpha, beta, take values plus or minus. So the two R and S are the usual mode numbers. And then two complex bosons. But these are not the standard bosons. They have spin half. So the fermions have spin half, but these bosons also have spin half. So it's like a beta gamma system with spin half. So they have the now bosonic commutation relations. So you have psi and eta, and so you have commutation relations very much like that of the fermions. Okay, so these are the the defining commutation relations of the underlying fields. So psi and eta are canonically conjugate. I mean psi plus and eta minus, and here psi plus and sorry, I should have put psi. This is chi. So these are two different fields. There's psi plus minus and chi plus minus, and here you have psi and eta. So that's why there are two pairs of fermions which are canonically conjugate to each other, or totally four fermions and four bosons. So that's this thing. So this free field realization, in terms of this free field realization, actually these generate the generators of U1,1/2 at level 1 are bilinears of these fields. So this is, again, those who are familiar with SU2 level 1 will know that so let me, I've written this out here. Okay, so let me explain the different pieces. So these are the SL2R as before. These are SL2R. The SU1,1s pieces. These are the SU2 pieces. They will be denoted by K. These are the supersymmetries. The two sets of supersymmetries, the off-diagonal ones that I mentioned. and then there's our two U1s. So these are the two sort of U1s of the two blocks. So eta, so as I said, these are the eta and psi are the bosons. So the so the SL2R is made out of bilinears of the bosons. The SU2 is made out of bilinears of the fermions. So this is the most standard SU2 construction that you're probably seen. And the SUSY generators are bilinears of one boson, one fermion. And the U1 currents are the diagonal kind of U1s in both the, one is in terms of the bosonic U1 and there's a fermionic U1. Okay, so I mean, in terms of the fermions, they're both bosonic generators, but built out of, one is built out of bosons, one is built out of fermions. So this would, this SU2 and this U1 would be the usual U2 construction. And this is sort of the usual U1, 1 construction. And then these are the fermionic ones. Okay, you can now use these commutation relations that I had here. These commutation relations you can use to verify that these obey the current algebra of SU of U1, 1/2 at level 1. So the level is precisely 1. That's what the free fermions generate. So, so of course, like we do for SU2, we have to quotient out by U1 to go to this thing. So if we are going to go to PSU1, 1/2 level 1, we need to quotient by so there's actually, if you look at the algebra, you find that this combination Z, which is essentially U plus V, the sum of these two U1s, this is actually central. So if you actually quotient by this, namely you consider states which are annihilated by Zn, so n greater than or equal to 0, modulo Z minus n descendants, which are null, states. And so the Z minus n descendants of this n is greater than 0. Then you go to the PSU1, 1/2 at level 1. So this is the reason why. So the original system of free fermions and free bosons, you see, because one is a set of fermions, so this one will, there are 4 fermions, so it would have had central charge +2. These are 4 bosons, but they have lambda equals to, they have spin half. So they actually have central charge -half each. They just are opposite in statistics to the fermions. So they have a total central charge -2. So this this whole fermion bosonic system has total central charge 0. But then you do this quotient, the central charge of the PSU 1,1/2 level 1 is equals to 0 minus 2, which is -2. The -2 comes from essentially this quotienting. Okay, so so that's the free field construction. So now let's look at what this implies. So you remember at SU2 level 1, something very special happens. SU2 level 1, the only states that are allowed in the spectrum. So for SU2 level K, you know that the primaries are states which go from j equals to half to j equals to k by 2. But at k equals to 1, this means that there's only the j equals to half primary. So there's only one special primary. So SU2 level 1 is very small compared to SU2 level K. It has much fewer representations. And that's because there are null states at level 1, and so therefore most of the states are not allowed primaries. Similarly, a similar thing happens at SU2, PSU 1,1/2 at level 1. And one can see this fairly explicitly. So I just want to show that now. Okay, so there is a simplification. There's a vast simplification. In the spectrum of allowed representations. Okay, to see that, let's try to systematically talk about the representations of the k equals to 1 theory. So let's start with the NS sector. So here we define, so we'll first talk about things, no spectral flow, just affine representations of the PSU 1, the highest weight representations we'll start with. So in the NS sector, we have an NS vacuum. So you have a vacuum NS such that all these states, eta plus minus R, psi plus minus R, these are all equals to 0 for R greater than 0. Because R is now half integer in the NS sector, so I could have written this more precisely as R greater than or equal to half. So these are all 0. So maybe I should. So this thing, and so it's the usual way in which you would define for a free theory the NS vacuum. And if you, with the right definitions of these charges, you find that this is also equals to 0. So this is the kind of, in a way, it will be a trivial vacuum, but it is. It was there even in the Multisena-Oguri case. I didn't really mention it. It's the trivial vacuum. But what is more interesting is when you go to the Ramond sector. So now the fields are integer moded, and so you have 0 modes of this psi plus minus 0, eta plus minus 0, and then and these as well. Okay, so so we can label the ground state like in any remote sector, there's a kind of you label it by the occupation numbers of these zero modes. So you have a degenerate ground state. So
Rajesh, may I have a question?
Sure, yeah.
So you said the central charge is -2.
Yes.
So this should be non-unitary CFT.
Yeah, it's a non-unitary CFT, yes.
This NS vacuum state, which has a weight 0, cannot be the vacuum, right? There should be some negative dimension operator.
So in the NS sector, this is the vacuum, and so like I said, these are non-unitary CFTs. But when you impose the Virasoro, the physical state constraints, then that's when you will get you will get a spectrum which has no ghosts, which has no negative norm states, and where L0 is bounded from below, etc. And it is after you impose that this will become the vacuum of the ADS.
So if you don't impose this physical condition, then this theory,
then it's a non-unitary CFT. Yeah. So if you just view it purely as a CFT, then it is it's non-unitary. But it is like in any even in flat space string theory, if I have one time-like direction, then that's non-unitary. But the physical spectrum has no negative norm states.
Okay, thanks.
Yeah. And so we have zero modes of these modes, and we can label the ground state by well, before that, maybe I should say we can choose the psi +0, eta +0 to annihilate the ground state. So so as usual, the zero modes, when you have, they form like pairs of creation annihilation operator, and you can choose two of them to annihilate the ground state and two of them to act as creation operators. So now you can, and similarly, we can choose also psi +0 and chi +0. Also to annihilate the ground state. So now we can label the ground state by the other quantum numbers. So these are the creation annihilation operators, the plus mode. So we can label them by the minus mode. So so we label the ground state by the occupation numbers of, let's say, the psi 0 minus and eta 0 minus. So I'll call them M1 and M2. So these can be any integers. You can have psi 0 plus or minus, take integer values. And then you can, of course, you have the fermionic generators. So so for each M1, M2, we have a doublet. We have an SU2 doublet, which is basically the state M1, M2, and the state where you act by this chi 0 minus and psi 0 minus. So you have a Clifford algebra. So you have a doublet of SU2, and there are actually two singlets. And the singlets are the other states where you just act. So this is in some convention where we have chosen the ground state to transform non-trivially. And
so here eta, is it the like a Grassmannian even cost or?
Sorry, is?
This eta.
Yeah. Yeah, these are M1 and etas are the bosons, yeah.
Boson, but is it like a Grassmannian even cost? You said it's more like a beta gamma system or frequency.
Right. So it has commutation relations, but so it's like a beta gamma in the sense that it has spin half, but it is bosonic.
Bosonic. So it's not Grassmannian even variable.
It's Grassmannian even. That's why it has commutation relations, but it has spin half. So beta gamma is like that, right? Beta gamma is system are bosonic fields. They have commutation relations, but they would have, for instance, integer spin. Sorry, half integer spin, like for the case of the super diffeomorphism host. So it's a bit like that. Yeah. So beta gamma system, but with half integer spin.
So M1, M2 is also, I'm already confusing, like M1, M2 is also C number, like, I mean.
Yeah, so this is basically, this is the usual harmonic cost. So you just think of these as some creation annihilation operators, and then these are the occupation numbers of the different, the sign naught minus and sign naught plus. So because their commutation relation is just like that of a boson and I mean so you can think of sign naught minus and eta plus are the canonically conjugate. They will have some AA dagger like commutation relation and the other one similarly, and you can choose. So I've chosen some convention in which these two are the creation operators and the other two are annihilation operators.
Okay, I was confused. Yeah, thank you.
Yeah, so that's the statement that these are annihilation and then these are the creation operators. And you label them by their occupation numbers. Okay, so but then you also have the fermionic Clifford algebra. So this is the Clifford representation of the fermionic occupation numbers. But that's a finite dimensional vector space, but these are infinite dimensional, M1 and M2. Now you have, if you want to look at the PSU 1,1/2 representations, we need to impose Z0, which is that it should be annihilated by this charge, right? This is the central term that I said, which projects out this thing. So yeah, so I should have said one thing over here, that the J30 acting on M1, M2 is equal to, essentially it's M1 plus M2. I think I have to, there might be a plus or minus half, but in any case, I don't have that in my notes, but I think it's essentially M1 plus M2, maybe with a plus or a minus half. So what I want to say is that this combination M1 plus M2 is essentially J30, and so the and U0 is equal to M1 minus M2 minus half. Sorry, U0, I should have said it. And V0 is the fermionic one. So V0 will be, so in fact, let me write it, yeah. Here for this one, V0 is equal to 0, and for this, V0 equals to half. So remember, V0 was just some kind of a U1 generator. U0 was the U1 generator for the bosons. This was for the bosons, U, and B was for the fermions. The combination U naught plus V naught, you will need to impose that this is equal to 0 on all physical states to get to PSU 1,1/2. And I've written now what the in terms of this M1, M2 basis, what the eigenvalues are for J30, U0, etc. But you see from this that the V0, which is essentially the fermionic occupation number, that's essentially fixed. Depending on whether you consider this set of states, it's either 0 or half. So U0 is also fixed to be either 0 or half. Or minus 0 and minus half. So in other words, M1 minus M2 is fixed. So this implies M1 minus M2 is fixed. Right? Because you know that U0 plus V0, you need to impose. So M1 and M2 are not arbitrary. If you are looking at the PSU 1,1/2 representations, M1 and M2 will be either half or 1 or something like that. So it takes discrete values, a couple of possible values only. And corresponding to that, the J30, this is what we call lambda, remember. This is not fixed at the moment. This can take any values. And there is, so what you have is, if you now work out the Casimir, if we, or equivalently, we can see that if you work out the Casimir is the simplest way to see this, that the Casimir for this representation has C2 J is equal to 1/4, which implies J is equals to half. So essentially, at least for the ground state, and then there are some descendants which have J equal to 0 or 1. So this is the important thing, that you get this J takes this value half. So that's fixed completely by the representation theory. I mean, the free field realization tells you that the J value must be half. And this is not surprising. I mean, maybe you might have gotten a little lost in what I said, but you see from here, the SU2 representation, it's either V0 is half or V0 is, I mean, it's an SU2. There are only two representations of SU2 that appear, doublet and singlet. And the SL2 representation is tied to the SU2 representation by this condition. So this condition is very important because it connects the SU2 with the SL2R with the SU2. The bosons with the fermions, that you impose that they are correlated, and therefore you find that there's therefore the bosonic representation is essentially also J equals to half, like the SU2 representation. So this is the thing that's very special about the K equals to 1 theory and the free field realization, that only J equals to half is allowed. And basically this plus its super multiplet. So the Casimir for the SL2 representation has this thing. Actually, you can work out the super Casimir and it vanishes. But this is the representation that is the only physical one. So this has an immediate implication that So which is very important, which is that instead of the continuous families, C Cj lambda with j equals to half plus IP, one has only C half and lambda. So lambda is not fixed, but j is fixed to be half. So there is no radial momentum for this. So this P is 0 over here. And in fact, you also do not have, one can show that you do not have any, the dj, sorry, the d plus j, because the state that you have here is not the highest weight state of SL2R. M1 and M2 go from minus infinity to plus infinity. So, so you get actually a continuous family of this thing. So no, because there's no state annihilated by J0 minus for generic lambda. Okay, so so this is the most important conclusion from this free field realization, that that the spectrum of possible states in the k equals to 1 theory is much smaller than, is much smaller, because you lost that whole continuum and all the other discrete representations. So compared to the generic k greater than 1 case, it is, so all the long strings, no long strings with momentum. With a non-zero radial momentum, only in some sense the bottom of the continuum is there, and no short strings either. So almost a topological theory. So we only need to consider with so you can you only need to consider the spectrally flowed states which have built on this j tilde equals to half, and with different amounts of spectral flow. So you have so far everything I said was without spectral flow, but what you can now whatever representations that you have without spectral flow, you can now carry out the spectral flow like I described earlier, and consider now those representations in terms of these tilde modes built on the states with j tilde equals to half. But let me talk about the spectral flow in the language of these free fields, because that will be very important. So spectral flow, So, but before that, are there any questions?
So I have a question. Why are you saying that this is almost a topological theory?
Because we have lost most of the physical states compared to the k greater than 1. Yeah, I will try to flesh it out. At the moment, it is just a vague qualitative statement. But the reason for that is that we have, you compared to the k greater than 1 theory, we don't have most of these states which give the continuum. We don't have these short string states, only the states with j equals to half, which in some senses sort of measure 0 in the set of all the states that we had for k greater than 1. And there will be other reasons why it will also be. So in some ways, these are like some 0 mode states because
Okay.
they are like p equals to 0. There's 0 momentum. They're like 0 mode states. So there will be many senses, but this has not been completely fleshed out. But I believe there should be a very precise sense in which the k equals to 1 theory can be described as a topological sigma model, topologically twisted sigma model. But this has not been completely fleshed out yet.
All right. Okay. Thanks.
I want a question. So
Yes.
if this level k is integer,
The level k is an integer because it's related to the level k of the SU2, and that is integer quantized. Or from the point of view of the NS-NS flux, that's also an integer quantized. So
if k equal 2, for example, then what is the representation?
yeah, k equals to 2 is sort of, I call it semi-topological, because I think now the SU2 has level 0 in the NSR formulation, and there's only SL2 but I think the continuous states are still present. There's no, you don't have, so there may be some simpler representation of the level 2 theory. It has not been explored, but I think it's an interesting theory. It's somewhat in between you lose some states, but not all states.
But in general, in SU2 theory with level k, then the spin, allowed spin is from 0 to k over 2.
Exactly. So here you will have also, I think, some truncation, but it will not be, but I think it will be, you can still have things which are with momentum not equal to 0, I think.
Right. So this 1/2 is now generalized to k over 2.
Well, here, remember, we are talking about the SL2R quantum number. For the SU2, there will be some relation, but it's not completely obvious how the representations of SU2 and the SL2R are correlated. In general, it's not a very simple relation, but in the case of the free field realization at level 1, there's a direct correlation. So you're right that the SU2 piece, there will be only up to k by 2, but how that will translate into the SL2R representations is not completely.
I see. So representation theory for higher k is not well understood at this moment.
So I think the description of Maldacena and Uburi will still hold. So they give they give a complete description for k generically for generic k. So for generic k, there is no reason to expect any truncation, but k equals to 2 is slightly special in that the SU2 part becomes trivial, but I think the SL2R part is not trivial, and so that will continue to have representations, but they are not correlated with the SU2 representations.
Okay, thanks.
Yeah, so the spectral flow has a simple generalization for the free fields. So this is, you can again define like before. in terms of tilde variables. So you get psi tilde. So, just like I defined in terms of the tilde variables for the currents earlier, I'm claiming that if I define these tilde variables for these free fields, so they essentially are moving the mode number up and down by W over 2 for W units of spectral flow, then the bilinears built from these tilde fields have the same spectral flow defined earlier. So remember, I defined the J. So we here I wrote how the J's are built out of bilinears out of these fields. What I'm saying is that you apply spectral flow on these individual fields that will lead to a spectral flow on the bilinears. That will be exactly the same as what I had written earlier, except that just a small difference is that there is also spectral flow on the SU2 piece, etc. So you'll also have something like K3 tilde is equal to K3. These are the SU2 generators. So I can also define, so the spectral flow that I've defined over here will also lead to spectral flow on these, which on these SU2 generators. And also on the supersymmetry generators. So earlier I was mainly talking about the the bosonic generators, but here now I can talk about the super generators. So there will be still the the details will not be so important, except maybe for the Virasoro. Now, because I have spectrally flowed on both the SU2 and the SL2, the expression is slightly different from before, but it's very similar. The SU2 piece, the spectral flow, like I discussed when someone asked yesterday, it doesn't really do much, but it's useful to do it in a way such that both sides are spectrally flowed. So as I said, we will consider the J
So here W or omega is it even number, even integer, or
no, it can be half integer. So in fact, that's a good point. It can be half integer. So you can actually go from Ramond sector to NS to to the NS sector. In fact, the first non-trivial flow is sort of from you can define as one taking you from the Never-Schwarz sector to special Ramond sector.
I see. It can also go to the NS to the NS when the omega is even.
When W is even, it will take you from NS to NS, but with sort of, yeah. Exactly.
Just a small question for,
Yeah.
so we have this C0 equal to U0 plus V0, and we equated that to 0 before the spectral flow, right? So does that also hold after doing the spectral flow?
Yeah, so I should have mentioned the Z is actually invariant under the spectral flow.
Okay, because we haven't considered a highest, we don't have a highest weight state. So how is that?
But the Z is, you can look at this combination Z, which is U plus V, and U and V are defined like this. You can check that this is invariant under the spectral flow. So the spectral flow is an automorphism of the PSU 1,1/2. It does not change the U and the V generators. The generators of the additional U1, it doesn't change. So, so this, yeah, so that's an important point. I should have mentioned that. So, so you can impose Z equals to 0 before spectral flow, and it will continue to be preserved after spectral flow.
Okay, thank you.
So, so the J equals to, we'll consider this J equal to half, which in some sense you can think of as a short representation, and it's spectrally flowed images. Which are with J tilde equals to half. And so what that does is just that, yeah, in fact, the spectral flow is much easier to understand in the language of these three fields, because what it does is essentially things which were kind of positive modes become negative modes. And so now some things which annihilated earlier will not annihilate anymore. So you're kind of interchanging the role of creation and annihilation operators for some finite number of the modes. So it's a different representation. It's sort of a non-standard representation from that point of view, but it's easy enough to realize in this free field case. So. So this is what we have, and we'll now compute the full partition function. So what I will now try to this thing is the sort of partition function of the K equals to 1 theory. So what I want to do now, I will just sort of motivate the answer, but what I want to do is to tell you what the physical spectrum of the K equals to 1 theory is, and then match it with the symmetric dual. And we'll claim, like I said in the beginning of these lectures, that the dual is the symmetric product CFT at the free point, and we will be able to match the spectrum with that of the CFT. So now we have more or less most of the ingredients ready to sort of put that together, but I've also reached 12 o'clock. So can I just again take a little more time, Jungi, to maybe write down this partition function? And
yeah, of course, yes. Please.
Okay.
Yeah.
Thank you. So the partition function of the K equals to 1 theory, remember the full string theory I said a little while ago, it has in the general Berkowitz formulation, the full string theory has this Westerminowitten model, which now we are taking at level 1. In terms of these free fields, there's a topologically twisted T4, and then there's a set of ghosts. So I will write down the partition function to write down the worldsheet. In some sense, we are writing a worldsheet generating function of all the states, and we'll impose the physical state conditions. So this I'll write down for each of the individual pieces, and we can then put them all together. So the first piece is that of the PSU 1,1/2. Level 1. So that's the first part. So this is relatively easy to write down because we just have the character of 4 free fermions and 4 bosons. But we actually quotient out by Z, so that gives you actually 4 fermions plus 2 bosons. So that's why we remove the central charge of 2. So anyway, we can write down, so let me write down the partition function. So for a given representation, the character really of a given representation labeled by lambda, remember this is for the contribution of the C j equals to half lambda piece. So there's so the m quantum number is you sum over m with some chemical potential. I'll explain the chemical potential. And then you have essentially some free fermion partition function. And in the denominator, you have 2 bosons. So 2 etas come with the thetas, 2 thetas, and then you have 2 more etas. So this is essentially the character. So this is coming from the 0 mode sum, and these are from the non-zero modes. And so the 0 modes give you this. So I should write what the chemical potentials are. So X is e to the 2 pi I t is the chemical potential for J30. So that's why the m lambda, I mean, it's essentially m, which is lambda plus this thing. Then e to the y, which is e to the 2 pi I z, it corresponds to the SU2 chemical potential, K30, and tau is the q, which is e to the 2 pi I tau, corresponds to the L0 on the worldsheet. Okay, so you should think of T as the space-time torus modulus, because that's the space-time. I mentioned yesterday that this was the space-time L0. So you can think of T as the space-time modulus, tau as the worldsheet modulus. So this is essentially for the spectrally unflowed sector, but upon spectral flow, we will have, so if I look at the Wth spectral flow, then that's quite easy to read off from this. It's basically, let me write down the answer. It's the same thing. Most of the things remain unchanged, except this prefactor becomes and then it's just the same thing as before. So this is, remember on spectral flow, we have L0 tilde is equal to L0 plus W times J0. So, so once you do that and you rearrange the terms, you can see that the only effect is basically to give this addition. So W equals to 0, it reduces to the previous answer, but this is for non-zero W. There is this extra piece. Okay, so and the other thing to note is that this zero mode piece, which is the sum over m x to the m q to the minus mw. So this m is z plus lambda. This can be written as using the Poisson resummation. This is actually a sum of delta functions. So remember, this is the worldsheet modulus, the worldsheet torus modulus. This is the space-time torus modulus. If I think of a thermal circle and the space-time in the ADS, then the boundary will be again a torus, and this is the space-time modulus, and they're related actually by an integer. So W is an integer. So this is actually another sign of a sort of a topological string theory, because you have in fact holomorphic maps from the worldsheet to the space-time, which correspond to this delta function localization. So so that's another signature I just wanted to kind of mention, but we'll write it. This is the form that we will kind of okay, so that's the first part. The second piece of the so we wrote down the PSU 2,2, then there's the character of the T4, of the twisted T4. So that's the standard T4 supersymmetric partition function, except that now you have to look in the Ramond sector, because that's what the twisting essentially does. So that is a standard form. I'll just write down. So this is now not just the character, I'm writing the full partition function here. So I'm going to, so there are 4 fermions, 4 bosons, and then there's a lattice sum also. So this is the lattice sum for the, but that won't play any role, but that's the standard one. So this is like the Ramond sector partition function. So this part is straightforward. And finally, there's the character of the rho sigma course. And this we read it off somewhat indirectly, because you can actually go back to the NSR formulation, and where you can work out what the ghost contribution is, compare it with the hybrid formulation, and because for k greater than 1, the two are equivalent, and the ghost piece doesn't depend on the level k. So you can do that and read that off, and yeah, a final answer is again very simple. So I'll just write it down without going into much of an explanation. So what it does is basically it cancels against two longitudinal bosons. And that's the sigma ghost. Remember, I said the sigma ghost was the BC ghost system. So the BC ghosts, you know, their job in life is to cancel the longitudinal and time-like degrees of freedom, and so reduce two bosonic degrees of freedom. So that's what this eta, two factors of eta squared do. And for fermions, and that's essentially the super diffeomorphism ghosts, what it does. The other row, so this is what there were two ghosts, the rho ghost and the sigma ghost. So that's what the four fermions in the denominator essentially tell you. And so this is something you can argue explicitly from of the theory for k greater than 1, like I said. But now you see, if I put all these three things together, so let me. Oops.
I didn't get that. Could you try again?
Oops, sorry. Siri started talking. So let me. So you have these three pieces, right? And you have to take the product of these three pieces to sort of, well, I should have said, you should take the mod square of this, and these I've already taken the mod square. And you have to sort of multiply them all together. So you see that essentially this part cancels with this. So this part over here, when you take this and the left mover, that cancels with this. There's eta to the 4 in the denominator, and then there's the same theta functions. So essentially that ADS 3 times S3, all the non-zero pieces are cancelled by the two bosons and the 4 fermion. So, and you're essentially left with some zero mode pieces from the ADS3, as well as the full T4 partition function. Okay, so is that clear? So
is this a partition function or a character?
Well, it is the character. Well, I mean, I use the words a little bit loosely. These are actually both partition functions, and this one is a character. But then you take the mod square and mod square of the characters, and that will give you the partition function.
So part B is G of T4. Is that partition function or character?
It's the partition function.
But the second term is a lattice sum term, has only tau dependence. It's only holomorphic part.
No. Yeah, sorry, I should have written it more carefully. Yeah. Let's see. This should be tau bar. In fact, let me write it out. This piece is essentially what you would write as sum over p left, p right, q to the p left square, q bar to the p right square.
Okay.
Maybe. Yeah. So that's what the these things are. So let me so we can now put everything together. So you take so put A, B, C together. So essentially C cancels against the non-zero pieces, non-zero modes of A. And so you're left with so in the W spectrally flowed sector, the K equals to 1 theory, you have Z, T, tau, and their complex conjugates. So I'm sort of suppressing that. So that will be equal to summation M. And this Ramon sector partition function of the T4. So essentially the T4 piece, and this is the ADS3 zero mode pieces. So this is the ADS3 times S3 zero mode. So that's why it's sort of topological in this sector. And this is the twisted T4 partition function.
Sorry, I'm a little confused. Shouldn't you sum over omega somehow?
Yes, yes. We will have a W, you mean, right?
Is it W? No. Yeah, the winding.
W, yeah. So this is the piece for a fixed W, and then you're right. The full partition function is okay, so we'll have to do that sum, but actually, yeah, we don't. We will see that when we match, we will be able to match by sector for each W. So with the symmetric orbifold, so I won't really need to do the sum over W. I just want to. I'll just do a couple of steps and then leave you. Which is that this is, of course, the partition function, but we have yet to impose the condition, the Virasoro condition. So we can impose the Virasoro condition, namely and that L0. Now, of course, you need to consider the full thing. So you see that if we take a term Q to the H, some oscillator, some excited state in the T4 partition function, in this piece over here that I just mentioned, then the L0 condition implies then the L0 condition is that basically H oscillator and minus this piece is equal to 0, and similarly one for the L0 bar. But let me just look at this. So this implies that M, which is this something that you sum over, the J3 quantum number, is fixed in terms of the excitation. So this is how the lambda or J3. So this fixes lambda or J3 0. Because remember, M is essentially the J30 eigenvalue. And note that it's also not always a half integer, etc. So what we can do is, so on shell generating function of states we can is given by replacing q, which is equal to e to the 2 pi I tau, we can just replace by e to the 2 pi I t by w, because you see effectively where you had this q, now you will have all that happens is that you replace that by x to the m. So and x to the m will have a piece involving h oscillator by w, and x is e to the 2 pi I t. So effectively, all you have to do is just replace this thing. So the z for this zw on shell, this is equal to, this is x to the w by 2, x bar to the w by 2, and then you get this partition function. So, what I've just essentially done is basically made this replacement in this partition function, and that is what imposing the L0 constraint does for you. And when you do that, all these prefactors essentially simplify, and you get x to the w by 2. And wherever there was a q, you can replace it by basically x to the power 1 over w, and that's why we have this dependence over here. Okay, so and then that I should explain what this prime means. The prime refers to the condition. It's like the L0 minus L0 bar, because the lambda is the same on both sides. So you get w by 2 plus h. And this is essentially lambda bar. So basically, this is a level matching kind of condition on both sides, which tells you that this is equal to, this is congruent to 0 mod w. So that's what this prime refers to, that when we consider this torus partition function, we keep states which are invariant under this. So therefore, we can write the z total now at k equals to 1, and you can use some identities of theta functions to rewrite this in a slightly better form. And the even and odd pieces have slightly different. Okay, so basically what this means that this is like the same as above, which involves theta 3. This involves theta 2, and this involves theta 3. That's essentially what the subscripts R and NS mean. So so that's the final answer for the partition function. Okay, so I think I've gone over half an hour. I should stop here. If this was a little fast, I can explain right now or at the beginning of next lecture, whichever. And so this is the answer that we get for the k equals to 1 partition function.
All right, thank you very much for the very nice talk. And is there any question?
So can I ask a question?
Yeah, sure.
Yeah, so just to make sure, so this spectral flow sector corresponds to like string winding on some circle?
That's how you can view it, yes. I mean, in the sense that when I drew this picture, the picture from Madhusena Noburi at the beginning of this lecture, I mean, the idea was that there is a winding here by W, but notice that it's not a conserved quantum number in ADS3 because this is contractible. Right. So things can actually, so you can label the spectrum by this number, but it's not conserved by 3-point functions, by interactions.
I see.
So
okay.
It's not strictly speaking conserved winding, but it is a winding that you can think of, an asymptotic winding, and that's what you can think of over here, which will become maybe more clear next time, asymptotic winding of this world sheet over the boundary sphere. So supposing I'm working in the Euclidean case where I think of ADS3 as a ball whose boundary is 2 sphere, then I can consider maps from the world sheet, which is also a sphere, to the boundary sphere wrapping W times.
Okay.
So
okay.
so that in that sense it's a winding. Yeah.
Okay. And also the partition function can we compare with some known results in the literature?
Yes. So that's what I will. I had hoped to do that today, but I think since it's so this will turn out to be exactly the same as the orbifold CFT partition function, that of the single particle states of the symmetric orbifold CFT. So that's why I wrote it in this slightly different form.
Okay.
So this answer is exactly the spectrum of states. So this, remember, this is the on-shell spectrum of states of the string theory, the perturbative states. It's all the states I'm claiming of the string theory at k equals to 1. There are no other states. So it's the full spectrum, and I want to compare this full spectrum with the spectrum of some dual CFT. And that's what I will do in the beginning of next lectures, show that the symmetric orbifold CFT has essentially these sectors, and this W will refer to the sort of cycle, the W twisted sector of the symmetric orbifold. And so for each W, there will be a match W for each W, this piece or this piece, depending on whether it's even or odd, will match with the corresponding sector in the symmetric orbifold.
Okay, thank you.
Is this W is a number of the D1 string in the CFT side?
Yes, you can think of it, well, it's a long string of length W. Yeah, I mean, you can think of it in that way. There will be W cycle twisted sector from this orbifold CFT side.
Okay. And another question regarding this, your comments on this topological theory. Do you expect that in the ADS 5 context, you know, that the tension is corresponding to this free CP-MU theory? Do you think that it somehow is also can be characterized by some topological theory?
Yeah, I think that case also there will be a topological theory. In fact, it goes very parallel to this particular case, as I will try to explain in my Monday seminar. It will be very parallel. So once you've sort of understood this, you'll see that the ADS5 case is a very natural generalization. And all the features, the topological features that you see here, have a reflection in the higher dimensional case as well.
Thanks.
So yeah, so free Yang-Mills in 4 dimensions is, I think, described by a topological string theory.
Is there any other question? I have very basic question about
Sure.
this Green-Schwarz like a hybrid. So usually, just in flat space, there is kappa symmetry.
Yeah.
And so here, is there also some sort of the generalization of the kappa symmetry in the ADS side?
On the, when you write in terms of the ADS, I mean, there's in the ADS3, this thing, these just become the, you've kind of gauge fixed it, so there's no, there's no additional kappa symmetry, or rather, the kappa symmetry gets transformed into some additional worldsheet gauge symmetries. So there's an underlying n equals to 2 string worldsheet symmetry. And that's what, in some ways, the kappa symmetry gets morphed into. So it's not, yeah, so it's not standard kappa symmetry.
I see. Okay.
Can I ask a short question? So for this level k greater than 1, so we start getting these short string spectrum in the spectrum as well, right? Instead of the continuous spectrum of long strings. So
you have both. So you have both the short strings, right, and the continuous spectrum of long.
So will we still be able to get a CFD that is dual to the spectrum that we get for k greater than 1?
It should be. I think there should be a point in the moduli space where you get a continuum, but what that point is, I mean, the parameters, the moduli space of this dual CFD is a very big 20-dimensional moduli space. And where on that moduli space you might get a singular CFD with the continuum of long strings, that has not been identified yet. Because we don't have that much control over the theory away from the orbifold CFD, away from the free point. We don't know what the spectrum really looks like. But presumably somewhere in that 20-dimensional space, there is some codimension, lower codimension locus on which you have a singular CFD.
I see. Okay, thank you.
So in this case, can you also compute the partition function?
In the k greater than 1 case?
Yeah, k greater than 1.
Yes, so this is what Maldacena and Oguri did, and there is an explicit form, but because of this continuum, you have now kind of a singularity in the, it's a singular partition function. That's another way you get continuum infinite integrals over the momentum. The center of mass momentum gives you a sort of a Liouville-like mode.
Mm-hmm.
So yeah, you can define the integrand, and the second paper of Maldacena and Oguri give the full answer, but it's not a finite answer like this one. It's a divergent integral, and so you have to make sense of that and maybe try to compare with a dual CFD.
Is there a way to regularize this somehow to get?
So Maldacena and Oguri regularize it, and you can think of it like there's a divergent piece is like that coming from a Liouville piece, but that's about it. I mean, you can kind of write it in some way which you can potentially compare it, but what it is compared to is not very clear.
I see. Thank you.
There is a proposal by Eberhardt and Gabardil where they want to make a connection with the symmetric orbifold involving a Liouville factor. But how that's connected to the symmetric orbifold moduli space here, it's not completely clear, but yeah.
Okay, I see.